In this video, we're going to prove the following theorem. Let the positive integer n be written in terms of the powers of the prime p so that n is equal to this, where the coefficients are strictly positive and less than p. Then the exponent of the highest power of p appearing in the prime factorization of n prime is what it says there. So basically, if you have p to this power, it will divide n factorial. But if you add one more to the power, it won't divide n factorial. What's in yellow for that power, that's the largest such value. P to that value will divide n factorial, but nothing larger. If you like seeing proofs of mathematical theorems and corollaries and lemmas, you should consider subscribing to my channel, as this is what we do here. We prove theorems. Now, we know that the largest power of p that divides n factorial is always the summation of the greatest integer function of n divided by p to the k as k goes from 1 to infinity. Now, k doesn't need to go to infinity. Maybe k just needs to go up to 8, because at some point p is going to be large enough where this is less than 1, and of course is going to be true for p sub k plus 1 and p raised to the k plus 2. So this implies that the greatest integer part, or the greatest integer function of n divided by p to the k will equal 0. Okay. So what we get is n, going to be the greatest integer function of n, which is ak p to the k, all the way down to a sub 1p plus a sub 0 divided by p to the 1. And then you're going to have ak p to the k all the way down to a1p plus a sub 0 divided by p squared, all the way to n. Now, I'm going to make one little change. I'm using k in two places, it seems. How about we call the power, the dummy variable for the power, m. So we have this up to a sub 0 divided by p to the k. Now, just want to comment on a lemma that I'm going to use, one that I've proven already. If n is an integer, n plus a, the greatest integer function of n plus a is that integer plus the greatest integer function of a. Now, if it turns out that a is between 0 and 1, that's going to be 0. N plus 0 is n. That is, you just get the integer. If this is between 0 and 1, this sum will be n. And that's going to come up a lot. So, in the first piece right here, we divide by p to the 1. So we get a sub k p to the k minus 1 plus a sub k minus 1 p to the k minus 2 all the way down to a sub 1p divided by p. That's just going to cancel out. That's all of this is an integer. And then if I add a sub 0 over p, this is less than 1. So that's like my n before and that's like my a. The greatest integer of this is just n. So I don't need to put the greatest integer notation or greatest function notation, and that's all good. Plus, now we deal with this. We have a sub k, p to the k minus 2, all the way down to, say, a sub 3, p to the 1, plus a sub 2. The next term is going to be a1 over p plus a sub 0 over p. Yeah, we're dividing by p squared. So that'll be p to the 1, and that'll be p. P squared. Okay. This is, oops, this here is less than 1. So the greatest integer part is 0. And we continue in this fashion to the very last one. And when you divide those two, you get a sub k plus a lot of other stuff which is less than 1. So the greatest integer part of a sub k plus less than 1, but positive, is just a sub k. So we don't need any of that. Okay, now let us factor out a sub k. How many do we have? Well, we have p to the k minus 1 plus p to the k minus 2 all the way down to 1. Plus, how many a sub k minus 1s do we have? Well, we have p to the k minus 2. Over here is going to be p to the k minus 3 all the way down to plus 1. And so on, all the way down to, say, a sub 2. So you're going to get p plus 1 plus a sub 0. A sub 1 will just be 1. Okay. Now, this is equal to, so recall that if you have p to the r plus p to the r minus 1 all the way down to 1, this is p raised to 1 more than r minus 1 over p minus 1. So this power in the first bracket is r minus 1. So I make it 1 more, a sub k. So we get p to the k minus 1 divided by p minus 1. Plus a sub k minus 1. We get p, add 1 to the power, k minus 1 minus 1 divided by p minus 1. All the way down to a sub 2, and you have 1 plus p. So it's p squared minus 1 for p plus 1. And if you don't believe that last one, the numerator fact is as such, and the denominator, like all the others, should say p minus 1. The p minus 1's cancel, and I get p plus 1. Exactly what a sub 2 should be multiplied by. And then we get plus a1. Now, times p minus 1 over p minus 1. Okay, so now let's distribute. First of all, everything's over p minus 1. So we have a sub k p to the k plus a sub k minus 1 p to the k minus 1 dot 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 all the way down to a sub 2 p squared plus a sub 1 p. Now I am going to add in a sub 0. I'll subtract it in a moment. Minus a sub k minus a sub k minus 1 all the way down to minus a sub 1. And as promised, to take care of adding a sub 0, I am going to take away a sub 0. And their theorem has now been proven, because that's n minus the sum of all the coefficients all divided by p minus 1. Exactly what the statement of the theorem told me to do. The only difference here is I didn't write some of the coefficients in the same order, but addition commutes. This finishes this proof. As always, if you like watching mathematical proofs, you should subscribe to my channel. Hit the like button. Tell your friends about my channel. Tell your enemies about them. See you guys hopefully in the next video. Don't forget, watch and learn.